with LIGO detection, but he also have some work related to the detection of still the mass compact binary mergers, or continuous wave, or stochastic backgrounds that's all the detectable signal within LIGO. So,
right. Thank you, Xinye. I'm delighted to be here, talking about a topic that's a bit more exotic than what I usually work on testing GR, but I think this is even more crazy in a sense. And as you're all aware, black holes remain, even after this latest detections by LIGO and much progress, mysterious objects, which is why we have an institute like BHI. But besides just studying black holes themselves, we can hope to use black holes as tools, as probes of new physics that is in a sense even more exotic or more unknown. And so in particular, that's the prospect I would like to lay out for you today. It's a recent, well, it's an old idea maybe, but it's an idea that has recently gathered a lot of attention and excitement from the theory and from the particle physics community and the LIGO community, that we can turn gravitational wave detectors into particle detectors. In particular, the main message of this talk, which I will break down for you as we go along, is that if an ultralight boson, so a new particle outside the standard model, exists, it will spontaneously form these clouds, microscopic clouds around fast-spinning black holes. The clouds will proceed to emit large quantities of gravitational waves that we can hope to detect directly with LIGO, and so by targeting gravitational wave searches to these sources, we can hope to constrain or detect the presence of these particles. So before we go on, I have to have the mandatory disclaimer that I'm not a theorist. My area of expertise is in this very last part of this project, so how do we detect these signals. But so you feel free to ask me questions about theory, but I reserve the right to shrug, and there's someone in the audience I'm sure knows the answer to. With that in mind, let me say a few words about why this is interesting and what do I mean by these conjecture new particles. An ultralight boson, for our purposes, is any integer spin particle that has a very light mass, and for us that means between 10 to negative 20 and 10 to negative 9 electron volts. These are well-motivated extensions of the standard model for very different reasons, among them that it could be a potential candidate of dark matter, but the most vanilla, the most famous of these particles is perhaps the QCD axiom, which was postulated back in the 70s to solve problems with quantum chromodynamics. You also have motivations from string theory to expect, or other high-energy arguments to expect a whole set of scalar and vector particles within this range of masses. I will not go into that because I don't have time and because I don't know anything about string theory. So the point is...
But for the dark matter, it's 10 minus 20 electron volt, and that scale is kiloparsecs of the de Broglie wavelength, isn't it?
Right, so
it's not relevant to black hole.
There are, so this, as we'll see, this mass range is corresponds to astrophysical black hole masses. People that work on fuzzy dark matter and those ideas go below 10 to negative 21 and so on. As we will see, yeah, maybe 10 to negative 20 is pushing it, 10 to negative 19 with Lisa we can do. I'll show you how this number comes in, but yeah, it is the quantum wavelength, as you said. So how to look for these particles without committing to any specific model about their interactions with the rest of the standard model. And keeping in mind that by construction, these particles effectively don't interact with anything. So the key idea is to notice or take advantage of the universality of gravity, and in particular use spinning black holes as probes through the gravitational interaction to unveil the presence of the particles. The phenomenon that links the bosons to the black holes is superradiance, which you may have encountered probably in a lot of under a lot of different guises studying black holes. This comes in the Penrose process, Hawking radiation, Blandford-Zinaik, a lot of different processes that rely on superradiance, which is effectively just the fact that waves may be scattered from a black hole with an amplitude that's larger than what they came in after extracting some energy from it. So the superradiance is usually presented as a specific, quite exotic property of black holes, but in reality you can understand it as a quiet, basic, dynamic effect. So I invite you to imagine you have a rotating cylinder with a rough surface, and it's rotating with some angular frequency omega. And if you flick a ball at it with some initial velocity, it will just hit the cylinder. And if the speed of the surface of the cylinder at the point of contact is larger than what the ball came in with, due to the friction, the ball will scatter out with more energy than it came in. It's just basic classical physics, I guess. And this will happen, so the ball will have more energy afterwards than initially if that relation of the velocities is satisfied. So if the velocity of the incoming ball is less than the speed of the surface at that point of contact. You can have the same phenomenon actually with waves, in which case the amplitude is what increases, and the condition that you have to satisfy is that the angular velocity, the angular frequency associated with the wave divided by the azimuthal quantum number has to be less than the angular frequency of the cylinder. And there have been experiments with this with superfluids and under different contexts, but it's the same underlying physics. So this is actually a global, sort of universal condition that the superradiance condition will tell us that if you have the scattering process where there's some dissipative process and this is satisfied, you can have a wave that's scattering with more energy than it actually came in, extracting it from the central object. It's generally very hard to observe, which is why, and the reason why is that you need very fast spinning objects, very symmetric also, to actually be able to have this condition satisfied with any kind of wave that you can make in the lab. But the most fast spinning asymmetric objects in the universe are black holes, and so you can think of black hole superradiance as a special kind of this more generic kinematic process. And in black holes, it's the same thing. You shine some light, or you aim some wave at the black hole, and if the same condition about relating the angular frequencies is satisfied, the wave will actually scatter out of the black hole with more amplitude than it came in, and the black hole will have slowed down, and in so doing, it will increase its area, and it will satisfy the second law of black hole thermodynamics. And so there's a whole richness to this phenomenon that I won't go into, but it's basically the same process as before. So how does this matter for us? Well, if on top of the usual particles in the standard model, there's an extra boson field, an ultralight boson field, so let's say it's a scalar particle with very light mass. The normal fluctuations of the field around the black hole will give rise to, you can think of pair production, except these will interact gravitationally with the black hole, and so they will scatter off it. If the mass of the boson field matches the mass of the black hole in a specific way, instead of just falling in, these field perturbations will scatter off with more amplitude due to superradiance, and you effectively increase the number of particles in that energy state of the boson. And this process happens over and over again in a runaway fashion, so it's an exponential growth of this, the occupation number of the field, in which the mass acts as a mirror that contains the particles in the vicinity of a black hole, just like in the Tucholsky black hole bond, which some of you might be familiar with, but I won't describe. So you can imagine just from this poor analyst's description of this rich theoretical phenomenon, that the maximum amplification, or the best that you can have for this process to happen, will be when the quantum wavelength of the boson is commensurate with the size of the black hole. And for astrophysical black holes, this gives us roughly this range. Perhaps this is too low.
And that lower range is for supermassive black holes?
Yeah, so
Stellar mass, it should be 10 mass.
10 to the minus 9, thank you. And this will be stellar and then supermassive. Yeah. Thank you. Yeah, I just changed this last minute. The point is that this is a theoretically interesting range of boson masses, if you put minus sign. And we can prove that by observations of these black holes, stellar mass or supermassive black holes. And this is a range of masses that is extremely hard, if not impossible, to probe with any other experiment. Anyhow, if you keep this in mind, that the quantum wavelength and the size of the black hole have to be similar, then you shouldn't be surprised that when you actually put in the math and you solve Schrödinger's equation on a curved background, you find that the boson arranges itself in energy states that are just like the hydrogen atom. They have energy levels that go as 1 minus a number alpha, and there's a series of them determined by the quantum number n, and they have radii just like in the hydrogen atom. Except that, unlike in the hydrogen atom, the constant that determines the size and the structure of these energy levels of the boson field around the black hole is not a constant of nature, but it's really just the ratio of the two scales. So the ratio of the gravitational of the size of the black hole to the reduced quantum wavelength. Yeah.
Are you assuming some specific spin for the black hole, or how does this depend on the spin?
This doesn't depend on the spin because it's perturbative, and to the linear to the first order it doesn't. It will come in that the spin comes in through the fact that you should actually be using spherical harmonics to decompose the angular part of the wave function. To next order than the spin, I think, will correct this. That's what I understand. So this is perturbative, right? This is.
But it's, you're talking about bosons that a lot of them can occupy the same state. So
Yeah.
how do you know what the occupation number is?
So the occupation number will grow from 0 to something. So we can compute what the rate of growth of the occupation number is for any given level. Just from solving the Schrödinger equation, you get the imaginary part of the frequency of the wave function, and you get what the rate of level growth is. And the level will keep growing until the spin of the black hole is small enough. So as the level grows, the black hole slows down, and at some point, this factor changes sign, which this factor corresponds to the superradiance condition that I showed earlier, and is no longer satisfied, and the process shuts down. So I'll show you right now a picture of this. Exactly. So these are bosons instead of fermions, so we can have an unlimited number of them in the same energy state. The system is non-Hermitian, and like in the hydrogen atom, so it will grow just spontaneously if this condition, the superradiance condition, is satisfied. What this means is that for a scalar boson, the fastest growing energy level will be the L equals m equals 1, which means that the energy density of this field will look like a dumbbell, basically, around the black hole. For some fiducial values, you get that it takes the whole cloud to grow a few hours to grow. It will have a radius of around 10 times the Schwarzschild radius of the black hole, and it can have up to 10% of the original mass of the black hole. So the picture, as I was just anticipating, is that you start with a very fast spinning black hole. Spontaneously, this cloud begins to grow of this energy level that satisfies this superradiance condition. The cloud keeps growing, and as it does, it takes away spin and a little mass from the black hole until the superradiance can no longer take place because the black hole spins not fast enough. At which points the process stops, and the black hole and the cloud effectively decouple in the sense of they don't exchange energy anymore. And we can compute what the final spin of the black hole is when that condition is satisfied. Anyways, once this has happened, you can forget about the black hole, but you have this giant, with this large microscopic cloud around it that will actually co-rotate with the black hole if it's a scalar, and it will emit gravitational waves. And this is the part that I'm interested in, because we can actually hope to detect them.
Is that formation time proportional to the light crossing time?
Yes, the formation time is, well, I'm not sure. I'll show you what the formation time is for different black hole parameters. And the answer, which is what matters to me, is that it varies with orders of magnitude, depending on how well the boson, and it's not just the light crossing time of the black hole, it has to do with how the ratio of the black hole radius to the boson wavelength.
Yeah,
so depending how good that matches, the faster the process will be.
The light crossing time is orders of magnitude smaller than ours, right? The
Right,
light
so I
crossing
guess
time will be
it's
like 10 to the minus 6 seconds or something, right?
Right, depends.
Anyhow, after this happens, the cloud will dissipate eventually after radiating all its energy into gravitational waves, and you're left with a black hole that is spinning but significantly less than it originally was. So the next part in the story is the gravitational wave emission, and there are several ways in which a cloud like this can be expected to emit gravitational waves. So the growth process is very interesting and so on, but what I'm really interested in is what's the phenomenology of these sort of systems, and there's a lot of rich observational features that we can try to detect. So as yep.
Will it also actually affect the binary black holes? Or?
Yeah, so that's interesting. So people have only just started looking at the effect that would have on the phasing of the gravitational wave, let's say, if the two black holes have clouds. But the expectation is that by the time the black holes merge, these clouds will have faded away because of the relevant timescales. Although maybe that's not true. But I won't talk about that exactly. But yeah, it's a good hunch. There are several ways in which a cloud can emit gravitational waves. I won't go into details. One of them is, for example, bosons jumping energy levels, just like in the hydrogen atom. You can have the whole cloud just collapse due to self-interactions and emit a huge burst of gravitational waves. But for the purpose of detectability, if you look at how likely these are and the time scales involved, the most relevant is what in the quantum picture would be two bosons annihilating into a graviton and emitting a coherent gravitational wave. In the classical dual description of this process, this is really just the stress energy of the boson cloud changing. So there's a quadrupole moment and it's emitting gravitational waves. So I'm a classical physicist and I like to think about it that way. There's a dual description of it in terms of the two bosons annihilating into a graviton. So,
why would we ever think about this quantum mechanically? Experimentally, we'll never see anything with an H bar, right?
Why would we think about it? Because
quantum mechanically.
yeah, well,
In the
you're
quantum
solely
mechanical
Schrodinger's equation and all that stuff. You don't need QFT maybe to describe it anymore. I'm more comfortable talking about it that way. The particle physics people that came up with this first are more comfortable.
But the Compton wavelength is comparable to the size of the horizon, so you must use a quantum length.
Yeah.
No. There's a coherent state of them, so it's
like a
the
superconductor or
it's the
something.
early superradiant instability just rephrased as a quantum.
Yeah, it's
I
a dual.
think it's an issue of pedagogy.
If you have a fact where you can't observe an H bar, it doesn't seem pedagogically wise to.
I think here the reason people
It's
like
just how you want to
quantum.
explain
But the
it.
Compton wavelength
That's
has
his choice.
H-bar.
But
Yeah, we definitely need the quantum description. To
No,
solve
but
the
but
equation.
it's a
But
coherent
in this
state out
one-
of it, so you don't see an H bar effect.
Well,
Right.
the quantum states have H-bar in them, no?
Yeah.
So there is H-bar.
But it's also true that the quantum state of the binary merger had H bar. We didn't see any quantum effects. It was completely adequately described by classical physics.
I think the answer to your question is at this point we don't have to, but it is to describe the evaporation process of the cloud. It's more suitable. It's easier to do in the quantum picture because you can talk about the bosons annihilating. Otherwise, in the classical picture, I'm not sure how you explain the process by which the bosons just radiate away into gravitational waves. Maybe there is some way of phrasing that purely classically. But
I think you said it, right?
Quadruple.
They just have a quadruple moment.
yeah, sure. But then what's that process by which the energy goes from the rest mass of the boson to the... Maybe I just haven't thought about it, but okay. Yeah, I think of it purely classically. That's my answer to you. Anyways, we can predict exactly what the frequency of this will be coherent gravitational waves. In LIGO and gravitational wave parlance, we call these continuous waves. They're almost monochromatic with a very slowly changing amplitude and frequency. The frequency will be given by it will just be determined by the mass of the boson actually, but because it matches the mass of the black hole, you can write it as a function of the mass of the black hole and this constant that tells us how good the match is between the black hole and the boson. And just from plugging in numbers in here, you can see that for LIGO,
So-
we'll be able. Yep.
This cloud of bosons, it's in a non-axis symmetric state, is it?
Right.
Why?
Well, no, it is. it's just the L equals M equals 1 the wave function has that polar structure.
Yeah, why is it not M equal to 0?
Oh, because that's not the energy level that satisfies the super radiant condition. That level doesn't get populated. So when there's an expression, which I'm not sure I had. Oh, well, this one.
Is that right?
Depending on the angular and quantum numbers.
Yeah, you need a finite M. Okay.
So it's sort of self-selected, like this one level is the one that will, if it satisfies this, it will be populated and the others won't.
And therefore, there is a varying quadrupole moment and it radiates.
So that's true for scalars. For vectors, the spin, so the intrinsic spin is 1, and so the fastest growing level is actually J equals M equals 1, but the L equals 0. So that's different. So you no longer have this picture, and in reality it's just a circle. It would be a circle in this picture. But then the bosons themselves have angular momentum, and so that's where the stress energy is. Okay, so this is the mass range that we are looking at. So LIGO can probe effectively boson masses between 10 to the negative 14 and 10 to the negative 11 electron volts by looking at stellar mass black holes. These signals can last a very long time. We can predict just from classical arguments how long it would take to radiate away the energy of this cloud. And it will have consequently a very, what we call a spin-up, so a very small upward change in frequency. So it's similar to our chirps in CBC, similar, not the same, but as the energy, because it's gravitationally bound, as the energy gets radiated away, it goes faster, and the signal increases in frequency a little bit.
The amplitude of the wave is very small.
The amplitude of the wave, it's very small because I have megaparsecs here, which for continuous waves is not very small, because we integrate over a long time. So I'll show you now what the horizons of the detection are, which is what I've been working on. Yes, so let's move on. One of the specific signatures that we can expect to see is actually detecting these continuous waves, which, unlike the CDCs that you're all used to, the compact binary coalescences, are very long-lasting waves, almost as single frequency and almost not changing amplitude, and they do have smaller amplitudes than overall. The strain they reach is way less than what a compact binary would, but they are on for a long time, and we can integrate for a long time and take advantage of that, and our SNR increases with the square root. So anyways, the program that I've been looking at with collaborators in this paper is to try to actually target specific known black holes, either from known like X-ray binaries or whatever black hole you know. In particular, we're interested in trying to follow up merger remnants. So we see a compact binary coalescence with LIGO on Virgo, and we know there's a new black hole that was born right there. We have a good idea of its spin, we have a good idea of its mass, and we know exactly its age. And so we can actually target or direct, in our lingo, one of these continuous wave searches at that point in the sky and see if there's a signal coming. If enough time has passed that we know that a cloud should have formed and this signal should be there, and if it's not, that sets a limit on the existence of a boson in that mass range. So for example, if you have a specific black hole, say you have 60 solar masses, and you start with a spin of 0.7, which, I mean, I picked this because it's consistent with the 15 and 14 remnant, then you don't know what the boson mass is. So you don't know if there's an actual new particle, you don't know what its mass is, and depending on what its mass would be, what the amplitude and frequency of the wave you would get from this black hole. So for any given black hole mass or any given alpha, as I'm using here, for any given boson mass or any given alpha, I'm fixing the black hole mass, you would land somewhere on this curve, say here, and that would tell you what the amplitude and the frequency of the continuous wave signal would be for that black hole and that boson. So for example, for this black hole, the best you could do is if you had a boson of 4 times 10 to the negative 13 eV, which would put you at alpha 0.179, which you land here, and it tells you have a frequency of around 190 hertz, of gravitational wave frequency, and the amplitude is around 5 times 10 to the negative 26, which is around as good as we can do with like for 1 year of integration time.
Would you have also a gravitational wave background from all the black holes in the universe? So is that more than the current limits?
That's also one of the observational signatures that people have looked at. We don't know. The shape of this the spectrum of this background is very distinct from the ones that we usually look for. So when you translate existing limits, you have to take that into account, and that's work in progress within LIGO. You'll hear about it, but yeah. So that's very interesting because all black holes in the universe with the mass matching the boson mass will ring up, and at different redshifts will give you this very specific curve. So that's another observational signature. For all the plots I'm going to show you, this is for the fastest growing scalar level emitting in the 2-2 mode gravitational wave, and that's what these glyphs mean if you're wondering in the following plots. Anyways, as you change the mass of the black hole and its spin, the boson masses that you can probe change, and the morphology of the gravitational wave signal also change. And so for higher black hole masses, you can get higher amplitudes, like orders of magnitude different as you change in orders of magnitude of the black hole mass, and lower frequencies, which makes sense because of the dimensionality of the problem. The scale is set by the black hole mass. So the different colors here are different initial spins. If you start at a higher spin, you can get higher amplitudes. If you start at a lower spin, not so much, and so on. And so we can predict exactly, given the black hole we have, what kind of signal we should expect. This is just another representation of this. So the peak amplitude, the peak gravitational wave amplitude strain that you might expect for a black hole of initial mass between 1 and 10 to the 4 solar masses and spin from 0 to 1 is given by the color. So here's the plot I showed you before. So this will correspond to the 150914 remnant. And all these values are at a fiducial distance of 5 megaparsecs.
So that spin is actually the spin after we form the black hole.
Yeah, so the initial spin of the black hole. So if you're thinking of LIGO, it would be the spin of the remnant.
The final one.
The final black hole. And then it's an I because it's before the superradiance process has happened. After it's happened, it's gonna get spun down. Yeah.
Why do you take 5 megaparsecs? Where is that coming from? Why? In our
Because
galaxy, we have 5 kiloparsecs.
I took that number because that's what gives you this amplitude, which is the threshold that we can detect.
Right, but you have in our galaxy black holes of this mass, and they are 1,000 times closer.
Yeah.
So why can't you constrain them?
Because they're too old. I mean, we can. So we can target them. So that's one of the things that I wanted to show in the end. But yeah, age is the problem. So if the black hole is too old, you will have expect this cloud to have gone, to have dissipated by now. So if we look at it and we don't see anything, then it's not a statement. We can't really make a statement. So in this plot, I'm showing you for that same 1514 like black hole, what the two relevant timescales are. So how long it takes the cloud to form. For 1514, it would be 39 days, and how long so these are rough timescales, right? It's not exact. How long the cloud would stick around emitting gravitational waves, and for this remnant would be 7.5 thousand years. So it's fine when we're targeting CDC remnants, but if you're targeting an old black hole, then there's no hope. But it depends on so this varies a lot with the parameters. If you're interested, I can show you the plots. There are changes with orders of magnitude depending on the spin and so on. Anyways, let me just quickly show you what I've actually done, which is we have algorithms that can detect these signals. This is just to show you, we simulate what this signal will look like. It has a specific morphology in the time frequency plane. It will evolve. It will have this increase in frequency, which is different from the searches that we usually do for continuous waves, because we usually target things like pulsars, which actually have a frequency that decreases with time. So we had to change things to adapt to these kinds of morphologies. We also had to take into account that there's a lot of uncertainty about the effect of the astrophysical environment, and even we don't really trust the theoretical approximations that much. So we have a very powerful hidden Markov model that can reconstruct these sorts of signals very efficiently, even when you don't know perfectly the properties of the black hole or even exactly where it is in the sky. So I just want to show you what we can use that to predict the sensitivity of our different detector configurations to these sorts of signals. So here it's in strain, but I will quickly translate that for you in terms of into a reach. So how far away can we see the signals? And that's what you see here. So the color tells you the horizon, so the maximum possible distance for an optimally oriented source and everything being perfect, how far away we'd be able to detect the signal after 1 year of observation with one detector, and in this case, designed advanced LIGO. So see, for 15 and 14, that happened too far away. So it's 11 megaparsecs. Scalar, so this is assuming a scalar boson, it's too far for us to follow up. But anything in the galaxy is well within reach. And of course, this varies with the black hole parameters, as you see in the x and y axis. The case is way better for 3G detectors. This should actually be 300 for Cosmic Explorer. It's 100 for Einstein telescope. And it's really, what you're seeing here is really just the design, the sensitivity curve of each detector just translated into a distance, taking into account redshift and all the different changes in the algorithm that we have to make to adapt for the fact that the signal's speeding up and so on. So this was this is the main result of this paper, I guess, in a sense, which is actually predicting demonstrating the feasibility of these searches and actually estimating very carefully how realistic it is to actually follow them up. So just as a summary, the horizon for these clouds is significantly farther than any other, for these types of continuous waves, we usually just target things in the galaxy. This is we can see them way farther. So all X-ray binaries will be well within range, but there are some intrinsic issues in targeting binaries if you don't know exactly what the orbital parameters are, and there's uncertainty in the effect of their environment and their age, so you might want to be careful interpreting whatever constraints you get out of that. The merger remnants would be ideal because we know exactly how old the black holes are. We know pretty well their parameters. As long as we see it with at least 3 detectors and we have it in an area that's around 30 degrees squared, we can follow that up very efficiently. But we would have to get lucky given the ranges that we have. We would have to be quite close, at least for scalars. I haven't mentioned vectors because they're less understood in terms of the morphology, but their amplitudes are up to 3 orders of magnitude larger. So actually the case for observing vector signals is stronger. So if there was a vector boson, it would emit stronger gravitational waves, but the whole process would happen way faster, and our current algorithms cannot handle those signals that are evolving at a faster rate. It's not a fundamental limitation. So you see my next paper will be how to change the algorithm so that we can target vector signals as well, which are more promising perhaps even for current detectors, given the louder intrinsic amplitudes. Anyways, this was the story that I tried to put forward here. I think there's a lot of excitement from both sides. So the particle and theory community are excited that we have this new experimental probe, even if we don't see anything that is an interesting result for any given black hole or other observational signatures, like the stochastic background that was mentioned. And for us in LIGO, it's exciting because we love to do a lot of science, and this would also mean that LIGO can take over particle physics, and we can do relativity, cosmology, particle physics, and soon take over the world, I guess. So that's all I have for you. Thank you for your attention.
Apology for the last comment.
Any questions?
Oh yeah, it's on camera.
Yeah, careful.
So there is actually one constraint you can put that will be much tighter than LIGO can do, and that's from neutron stars. So we have binary pulsar systems that have extremely good timing, and the size of a neutron star is only a few times larger than the horizon of a black hole of the same mass.
But the spin is usually too low.
You need an ergo region for this to happen.
No, because when you
no.
solve the levels, I mean, even for the hydrogen atom, you have high N levels, right? So you can populate, even if it's not a black hole, you can populate the higher levels, right?
But you need an ergo region for the super radiance.
Super radiance to populate the levels, yeah.
Well, but is it not satisfied by millisecond pulses?
If the boson has some electromagnetic also interaction, so that it can interact with the pulsar and extract energy from it in a similar
I'm
way.
talking just gravitation.
Yeah, I'm not sure if you can have gravitational superradiance from just a pulsar. Can
Why
you?
not?
No, I'm not saying not.
Well, so the metric is the same outside the neutron star, the same as the black hole metric.
Right, but it is
But
the
it's
ergo
outside
region
the-
problem.
yeah.
Right. In principle, I would just, my hunch answer is no because it spins too slowly, but maybe it's not true. For the black hole description, you are extracting the energy from the ergo region. So I'm not sure how that would happen in the neutron star case. Maybe there's another mechanism that you can extract this way, in which case yes. But yeah, that's interesting.
But typically the neutron star radius is a lot larger.
Well, it's 12 kilometers, and the Schwarzschild
The ergo
radius.
region is inside 2m. So 2m is really small.
No, but the Schwarzschild radius. If you have a 2 solar mass black neutron star, the Schwarzschild radius would be 6
6
kilometers.
kilometers.
So this is twice the Schwarzschild radius.
Yeah, but the ergo region is inside the Schwarzschild radius.
And you need
So-
that. It might not.
Right.
I see.
If you can make those bosons, as you say, you can get your high-end hydrogen states.
Right.
How do you make them?
How do you
Without the ergo
calculate it?
region.
Yeah.
Not less thank our speakers.
Thank you. It sounds crazy, but it's not.
It's not crazy as long as the bosons exist.
Right, but even if they're not, at least you can say they're not. That's also exciting.
Very good. So our second speaker is Miguel Campiglia. Miguel did his PhD in Penn State University, working with architecture, and now he's a faculty in Universidad de Montevideo. And we are very happy to have him today speak about higher orders of theorems and asymptotic charges.
Thank you very much, Laura. So I will be presenting work in collaboration with Carlos Gada. This is working. So let me start with some introduction. A series of articles from 2014 from here, the Stronger's group, offer a new perspective on soft theorems in scattering amplitudes and asymptotic symmetries. This was followed by many studies since then, and contact was made with various topics such as gravitational memory, soft hair in black holes, glass space holography. In many of these works, electrodynamics is used as a model where to test ideas, and this will be the context of my talk today. But yeah, probably my interest is more in gravitational physics, and I'm also very much interested in black holes, although so far I haven't got into that story. But I'm hoping to learn some during my stay here. So the plan of my talk, we will need to first introduce concepts through a very simple example and then describe our work. And please stop me anytime. So first I wanted to just say what these words mean through a simple example. So the example will be a non-relativistic point charge. The radiation field is given by this formula. We evaluate the acceleration of the particle at retarded time and project the acceleration on the transverse direction of where we are looking. And if we now consider the case of a particle that has a definite initial and final velocity, as in a scattering process that will be the context of interest here, then if we integrate this formula for all times, on the right hand side we just get the final velocity minus the initial velocity. And we can think of this formula as specifying the zero frequency behavior of the Fourier transform of the electric field. So if we this is telling us that if we look at the spectrum of the electric field, of the radiated electric field at zero frequency, it will have this term here. And this is like a baby version of this soft theorem in the context of scattering amplitudes that will be the interest for us. What we have is Weinberg's soft theorem. So let me describe it. So we have now a scattering process involving a total of n charged particles. This describes both incoming and outgoing particles, and there is also a photon of momentum k, and we look at the behavior of the amplitude as the energy of the photon goes to zero, and this is given by this formula where we have the amplitude without the photon and a multiplicative factor here that sums over all the external particles, and this factor here is the relativistic version of this factor here. So what about the second part? I was talking about asymptotic symmetry, so let me quickly describe what we mean by that. So first, a few words about these radiation fields. We are taking, when we are looking at radiation fields, we are taking R to infinity, keeping this retarded time constant, and x hat at the point, the direction of the sphere at a constant direction. And in this limit, the electric field decays as 1 over R and is transversal, so it's captured by we can think of as a vector field on the sphere. This index A here is denotes coordinates on the sphere, and this is just a change from the spherical coordinates to Cartesian coordinates. And the reason I'm introducing it this way is to introduce the notion of future null infinity. So I will just, for later reference, draw the Penrose diagram of Minkowski space-time. So we have here R equals 0, and when we take R to infinity, keeping this retarded time U equal constant, we reach a point on future null infinity. And similarly, and with this vector field, we think of it as living on this abstract manifold of future boundary of space-time. Similarly, by taking R to infinity with the retarded time constant, we go to fast infinity. Okay. So in the example of this non-relativistic point charge, the radiation field of the point charge, as we were saying, is given by the acceleration, and we are projecting here on the direction parallel to the sphere, and there is no incoming radiation. So what we were referring to as this baby example of soft theorem came from integrating this equation over all time. And now if we just move these terms to the left, we have this equation in the form of a piece that lives in the asymptotic future equals a piece that lives in the asymptotic past, and this will be the type of expressions we will be having, comparing quantities at the past, at the infinite past, with quantities at the infinite future. The last thing I wanted to mention is that if we take the sphere divergence of this equation and use the analog of Gauss' law at future and past infinity, one concludes that this relation is giving a relation on the radial electric field at spatial infinity. So let me introduce here spatial infinity as this vertex in Penrose diagram. And what this equation is telling us is that we first go to null infinity and then take u to minus infinity, or we can go the other way. We can first go to personal infinity, and then go to I to special infinity, and doing this these two limits do not commute but have a very specific matching condition that was described by Strominger, and this is underlies this relation with soft theory. And finally, a few words I have to say about these asymptotic symmetries. If we now integrate this equation over the sphere with some function in the sphere lambda, then the resulting quantity has interpretation of another charge associated to the asymptotic symmetry corresponding to a gauge transformation with a parameter that is non-trivial at infinity. Usually gauge transformations are not considered to be physical, but in the case where the gauge parameter is non-trivial at infinity, then this is considered to be a genuine symmetry. And so so this was just to introduce the terminology. And going back to the context of scattering amplitudes, what it was shown was that the conservation of this having these quantities that we call charges in the sense of nether charge, not in the sense of electric charge, having them to be a symmetry in the context of S matrix, it means that they commute with the S matrix, and it was shown that they are this condition is equivalent to this Weinberg-Soft photon theory. And this, as I described in the baby example, this charge can be thought of as capturing the radial electric field at I naught. So what we would like to, the message here is that the radial electric field at special infinity knows about the zero frequency limit of the amplitude. So I'm now thinking of this amplitude that has a photon with energy omega. I'm thinking of it as a function of omega, and we know, and we are finding that this radial electric field at special infinity knows about this amplitude. So the question we would like to ask is if we can get more information by looking at the field at the radial electric field near special infinity. If we can get more information.
In the limit of omega going to zero, it's actually static, right? So is this really a photon, or is it just the electric field that the charge has at that point?
Right. In the strict, yeah, I mean, it is describing, in this case, it is describing the very low frequency limit of the radiation due to the charges that. So if
but it's not just the electric field of the charges.
But it's still like I'm still looking at the radiation part of the electric field. So I'm still in this example of the non-relativistic particle. I'm looking at the radiation field, but just looking at the first term. If I'm looking at the spectrum of the radiation field, I'm doing an expansion in frequency. I'm looking at the first. This was being the first term in this expansion. And the question is if I can know. I mean. If I can know more about the moving away from this first being term, how much I can know by just looking at so I will address this question in the context of three-level QED, and one of the places where we use this three-level condition is that this amplitude as a function of energy admits a Taylor expansion. So basically, this is like the first term in this Taylor expansion, and the question is if we can get information about the next terms. So that's what we would like to explore, and I will first say a few words about what is known about these terms in three-level QED, and then describe how what is known can be what is the relation of this with this radial electric field at special infinity. to get a little bit ahead of where I'm going, we will later relate these coefficients here with the components of the radioelectric field in a 1/r expansion. So yes.
So if you want to use these sub-theorems, is it true that then omega should go to 0? I mean, it's related to obvious question. Is there any fundamental reason behind that you have to go to the soft limit, or it's just as a matter of simplicity?
What we refer to as soft theorems, they tell you what is the amplitude in this limit, and basically.
The wavelength, right? I mean,
Yes. So we are thinking of this amplitude as a function of omega, and so far we know what is the behavior. You are doing like an expansion in omega, and then this Weimer's theorem tells you what is the first term. If you could know all the terms, you could recover the full amplitude in some sense. But we cannot do that, and the question is how much we can get just by this type of idea. Yes.
This R dependence is basically multiples, just like if you have charge distribution that has not just dipole but quadrupole.
Right. So far here, I am not assuming any multiple structure on this, but then the field equations will impose relations. Yes. At this stage, I'm just writing like an ansatz for the electric field, but then the field equations. Yeah. Any other question? So let me then describe the terms we have. So as we were just saying, the first term in this expansion is given by this Weinberg's formula. The next term is also given by a similar factorization formula where there is a factor multiplying the amplitude without the photon, and now the factor involves the angular momentum of the particles. So this is a derivative acting on the momentum levels of the amplitude. And if we go to higher orders, it is no longer true that the term is factorized, but it was recently shown that it can always be written, the nth term, as a piece that is has a factorized form. So it is a sum over external particles times the amplitude without the photon, and this term involves now higher order derivatives of the external momentum. So it's really like doing like a Taylor expansion. And then there is a reminder term that has a particular dependence on the momentum q of the soft photon, but its dependence on the momentum of the scattering particles is undetermined by the analysis. So in a sense, all the non-trivial information of the amplitude is contained, or most non-trivial information is contained here, but we are not, we cannot access it through this analysis, and we won't be able to, unfortunately, say much about it. So now, from this expression, we have this formula that I just wrote down, that the nth term of the amplitude is given by this expression, and I'm just writing this as an equality, and now we repeat what was done for the leading and subleading cases in order to go from this type of soft theorem to describe it in terms of asymptotic charges. And what is done in those works is to integrate this type of expression along all possible directions of the directions of the photon, and this integration is being done with some smearing function with some weight, with some particular weight, and generalizing what is known for the first two cases. We take the weight to be so let me explain the notation quickly. So this set here refers to stereographic coordinates for the sphere giving the direction of the photon, and the formula here is for the case of a negative helicity photon. In that case, we should take this holomorphic components here. So this an arbitrary this is at some tensor on the sphere that is so far arbitrary. And so this will be like the label of our charges, this T. And the role of these derivatives here, what we'll do due to these derivatives that are acting on this formula. So again, this set parameterizes the direction of the photon, and this reminder had a decomposition or angular decomposition in the direction, in the sphere direction, that only involve the spherical harmonics up to a given order, and for this reason, this differential operator kills this reminder, and that allows us to have a formula that only has this only has this factorized piece. So we can then proceed in a complete analogy as the previous cases and define this integrated over the sphere piece of this term defines what we call a soft charge that involves the Fock operator associated to the photon, and this second term here defines what we call a hard charge, which is the action of this charge on a particle state should be given by the formula obtained by smearing this.
Sorry.
Yes.
Why is TZ to the n plus 1 on Rn 0?
Yeah, so basically so basically the Rn has this particular dependence on the photon momentum q.
I see.
And then
so it can only go up to some angular momentum, is it?
Right. So this term here exactly has the spherical harmonic decomposition of this Rn goes to up to L equals n minus one because of this.
So are you saying at the first two orders we have conserved charges for every spherical harmonic, but at higher orders that they're conserved charges, they're just only
for the lowest order, even for the subleading order, the charges start at L equals 1.
Right.
So then at the nth order they start at L equals n. We are projecting the lower.
This is just like the Aretakis thing, isn't
it?
The Aretakis charges, isn't it?
Well, that's something.
They also, yeah.
But you will make the link with the
I had a comment on the Newman-Penrose. I think it's Newman-Penrose, but yeah. I mean I know Aretakis, the Newman-Penrose. They for given n you are at a specific spherical harmonic. The Newman-Penrose. Here we are starting at the next. We allow all spherical harmonics starting at the end.
But it's the first, it's a subleading order.
Yes.
So the leading order is quantum mechanically exact. At the subleading order, there's some finite set of operators that can renormalize the symmetry.
Yes.
Are those affecting the symmetry at higher n?
Yeah, we didn't look at that, but I will imagine, because as you are saying, I'm looking only like pure QD, but if you have something on minimal capping, then this term here will be modified, and this will induce modification on these guys. So therefore, yeah, but I
So
will
you expect
imagine
quantum
that,
corrections to it.
right, but I will imagine the logic will go through, except that the form of this piece here is different in those cases. But we haven't really looked at that.
And is there an algebra of these charges?
And that's something that we have no idea, and we don't right know how to compute also. Yeah.
Do you have any interpretation for the charts or no?
I mean, they somehow capture like some higher order moments, but yeah, I haven't thought too much about the interpretation.
But they're conserved charges in the sense of some number associating with the incoming data equals some number associated with the, unlike the Newman-Penrose quantities or something, which are conserved along Scri.
Yes.
They're total conserved charges for like energy conservation.
Right. In the same sense, right. Any other question? So, how am I doing with time?
Good.
Have
still 6 minutes.
6 minutes left? Okay. So basically, to summarize, this near version of this high order soft theorem can be thought of as a consequence of having this charge that commutes in ETS matrix. And the next question was to understand this in terms of the radial electric field. So I don't know if I will just maybe go quick here because. So the idea now was to look at the expansion of the radial electric field, put the ansatz of a 1/r expansion, and then plug into Maxwell equations, and integrate. And this gives a series of equations that for a given, starting with the zeroth term, you can construct the following terms iteratively. And here, the technical assumption that was coming from this three-level condition was that the time dependence of the the first term to solve recursively this is the n equals 0 term. So we need to specify how the n equals 0 radial electric field varies with u as u goes to plus or minus infinity. And here is where we need to use that the in frequency space this admits a Taylor expansion as we did for the amplitude. And this allows to integrate these equations at u equals minus infinity and have an expansion of this form. So now in addition to the 1/r expansion, now I'm looking at the 1/u expansion as u goes to minus infinity. So this second index here refers to the 1/u expansion. And the last term that appears here is the term that is independent of u. This term is appears as a kind of integration constant as we are solving these equations iteratively. And basically the idea is that this integration constant that depends on the angle can be written using the field equations in terms of integrals at non-infinity. And the claim is that when one does so, this integration constant really give you the information of these charges that I described from the soft theorems, where the parameter t that we were using in the soft theorem side is related to this parameter lambda that is near in the radial electric field by this type of relation. So I was just describing the situation from the future null infinity perspective, and the similar discussion at past near infinity, then tells you that this interpretation of this soft theorem in terms of discharge conservation can be understood as this sort of matching condition or property of the radial electric field at I naught, now looking at these higher orders. So let me summarize. So assuming this strong follows along sky plus and sky minus, there is a tower of conserved asymptotic charges or matching conditions that generalize the one associated to the leading soft theorem. From the point of view of tree-level scattering amplitudes, they reproduce this factorized piece that was described for tree-level amplitudes. Beyond tree level, so now a word about beyond tree level. So we will use all the time that we have this expansion in omega, but beyond tree level that's not true, and interestingly, it was studied recently what is the subleading term. So beyond tree level, we always, this is still true. We have this first term here, given by Wember's theorem, but then the subleading is no longer, is now order, is of the order log omega. But is described by a universal factorization formula, and one question is whether this can be understood in terms of asymptotic charges. The other question is the symmetry interpretation of these charges. And one possibility is that they are, one could think of them as charges associated to large transformations which blow up at infinity. So maybe that's not very attractive possibility because they will be spoiling your followers. And then, we wonder whether one could extract more information, maybe from the point of view of holography. From that motivation, one may ask whether one could extract more information at I naught, in particular if it could be possible to somehow get information about these reminder terms. So, thank you for your attention.
Any questions? So maybe you could comment about the relation to the Newton rules.
What I was saying was that because once we have this identification, because if we put lambda here to be a spherical harmonic, then this will be 0 for L less or equal than, for L smaller than N, again because of this property that this set projects down the spherical harmonic up to a given L. And the comment was that these charges can be thought of as double infinity, right? We have, for each n, we have in principle a tower of spherical harmonics starting at L equals n, the ones below are 0, and the comment was that if I write this expression for L equals n minus 1, so the one below the one we are starting, that exactly corresponds to the Newman-Penrose charge. So for us, for our follows, all the Newman-Penrose charges are 0. And our charges are starting for the next spherical. But of course, these are, the conservation is in a different sense, of course. But that was the comment,
So there should be some connection which isn't very well understood between the symmetries and Goldstone bosons. So for at n equals 0, it's just the Goldstone boson is just the flat connection on the sphere at infinity. Now, you might think that if you specify the electromagnetic field at null infinity, that would completely determine the electromagnetic field in the whole space-time. But when you do the 1 over r expansion, you find that it's not quite true because of boundary terms. So like, you get equations like this one you wrote here, where you have the n plus first term is determined only up to an integration function on the sphere, which are the potential Goldstone bosons
I see.
for these symmetries. So I'm wondering if you've thought about that at all. What could be what could be the Goldstone bosons for?
So because this, what I denoted here, ERNN are these integration constant?
They're the integration
Yeah,
constants.
they are, but we are expressing them. We are expressing them in terms of data at non-infinity, and here we are assuming that there's no contribution from my class. So we are re-expressing them in terms of
right
in similar, yeah. And that's how we can compare with.
Somehow I would have thought it was the potential rather than the electric field.
I mean, I can.
Because these things must be invariant under any possible
Yes.
symmetries, right?
I see. And so this really is like for n equals. These are generalization of the type of relation that you have for n equals 0 for the leading charge, where you express. But yeah, I don't know much about
It's
the Goldstone.
it's the canonical conjugate to that, I think.
The one you're saying.
Yeah.
I see.
Another question? Okay, Miguel will be here until tomorrow if you want to talk to him. Thank you very much.
Thank you.